Welcome everyone to the January general meeting of the Kalamazoo Astronomical Society. So of course, since it's the January meeting, Happy New Year. It is great to have you all back. We had a relatively successful year of activities last year, even though most of them were, via Zoom, and here we are via Zoom again. But I got to say, for the January meeting, I don't mind at all, because typically attendance is usually kind of low for the January meeting because we all have to go out in the cold and snow and work our way to KMZ and all that stuff. But now we have 60 plus here on Zoom. Maybe more will follow. And of course, we have a terrific guest speaker tonight to kick off the new year. So without further ado, let's jump right into it. So tonight's guest speaker is a research professor in the School of Earth and Science Exploration at Arizona State University in Tempe. He is the director of the Ronald Greeley Center for Planetary Studies, a NASA-funded planetary data center at ASU. He is also the director of the NASA Planetary Elion Laboratory, which administers wind tunnels at the Ames Research Center in California. He is currently performing research in volcanology and planetary geology with a focus on planetary mapping, geochemical, and remote sensing studies. His current research focuses on planetary geologic mapping of bodies across the solar system and computer modeling of the physical and geochemical evolution of lava flows in a variety of planetary environments. He was involved in NASA's Magellan mission to Venus, the Galileo mission to Jupiter, Dawn's mission to the asteroid Vesta and dwarf planet Ceres, although personally I would call them protoplanets, but that's okay, and ESA's Mars Express Orbiter mission. He is a member of the Janus camera team for ESA's JUICE mission, which is the Jupiter Icy Moons Explorer, and he is currently deputy imager lead and co-investigator on NASA's Psyche mission, scheduled to launch this August. And of course, that's the topic of his presentation tonight. In August 2014, David was elected a fellow of the Geological Society of America, and asteroid 10461 D.A. Williams was named in his honor. And before we officially welcome him, I want to mention we will take questions after the presentation. So we'd appreciate it if you stay on mute until the talk is over, and he'll be glad to take your questions in. So without further ado, please welcome Dr. David A. Williams.
Thank you very much. Pleasure to be here to speak to the Kalamazoo Astronomical Society. I actually grew up in South Bend, Indiana, so that's relatively close to you guys there. So I'm very familiar with what it's like to live in that part of the country. So what I'm going to do as I share my screen here is there you have the presentation. That's some artwork about the nature of our mission, Psyche, A Journey to a Metal World. And there's an artist graphic of the spacecraft we've been building for the last 5 years or so. So what I'd like to do for my talk today is I'll tell you a little bit about the Psyche mission and our goals and objectives and instruments and how we're going to do the mission. But before we start that, I want to give some background about, the whole nature of NASA's Planetary Exploration program. And the first question that comes up is, why do we choose to explore space? And if you see this slide here, you can see there are a whole variety of reasons why we choose to explore space. And since you're all, amateur astronomers, you have probably a good working knowledge of science, so you understand this. Science to understand the nature of the universe, national prestige, great nations undertake great things, and space exploration is among some of the greatest. Security, national security, maintain the high ground, protect from adversaries. Economics, identify and exploit space resources to enhance national economies. Sustainability, to develop new technologies to better preserve Earth and its citizens. Education and inspiration, we want to inspire and create the next generation of scientists and engineers. And then, of course, survivability. We want to transform humanity into a multi-planet species. The reason why the dinosaurs aren't here right now is because they didn't have a space program. They couldn't deflect that asteroid that hit 65 million years ago in the Yucatan Peninsula that wiped them out. And the only way to avoid that fate is for humanity to become a multi-planet species distributed throughout the solar system. Now, what is NASA's role in space exploration? Well, when people think of NASA, they probably think of the space station or the Apollo program or the space shuttle, but that's just one small part of a much bigger part of NASA. So NASA is divided into four what we call mission directorates: aeronautics research, which studies the air transportation system to help move people and cargo around the Earth; the space technology, developing technology to actually enable people to live and work in space; the human exploration operations directorate, that's the part that involves the astronauts. So that's the space station and all the vehicles that take them up there. And then finally, there's the science mission directorate, and that's the part of NASA that funds all of the scientists and engineers who do the types of missions to study the solar system and beyond. And the science mission directorate is actually split into 5 divisions: heliophysics, which studies the sun; earth science, which studies the Earth; planetary science, which studies everything in the solar system except the sun and the Earth; and the astrophysics division, which studies everything outside the solar system. So the James Webb Space Telescope, which just launched, is being deployed this week. That is actually paid for out of the astrophysics division. The missions that I work on as a planetary geologist come out of the planetary science division. And then a new division that was just formed about a year ago was taken out of one of the other directorates and put in biological and physical sciences. So with that understanding, let's ask the next question: how do we explore the solar system? We mostly use robotic spacecraft because that's what you need to explore a lot of these places that are so hard to send humans to. But we actually do a what we call phased approach to how we explore the objects of the solar system. We do what's technically possible, what we have the engineering skills to do and build. We do what's affordable, what Congress will allocate money for us to do. We do the easy missions first, we accomplish them successfully, then we move on to the more complex missions. And as you go down this list over here, you go from the easy, less expensive missions to the much harder, more expensive missions. The easiest is what we call a planetary flyby. It's just a spacecraft launches from Earth, flies by a planetary object, takes pictures, transmits the data back. That's the initial reconnaissance. Next, you would send an orbiter mission, something that can actually get into orbit around a planetary body and collect data globally as the spacecraft orbits around the planet as it rotates underneath it. That gives you your global data set. You can globally assess a planet. Once you understand it from an orbit, that's when you want to land on the surface. And there's a variety of types of landers you can use. A hard lander is something that just descends and then smacks into the surface. So the instruments are broken, so they're not quite as useful. Soft landers are things that use retro rockets or parachutes or airbags to slow it down so it lands on the surface and all the instruments work, and you can take your wonderful 360-degree panoramas and your soil samples and everything like that. But what typically happens with those type of landers is you see something on the horizon and you're really interested in it, and so you wish you had mobility. So that's where rovers come in. That allows us to have mobility to move about the land, or if it's a body that has an atmosphere, fly through the atmosphere. And the perfect example of that is the Perseverance rover and the Ingenuity helicopter that landed back in February of last year, and have been exploring Jezero crater on Mars ever since then. The next most expensive, next hardest to do is robotic sample return, where you actually have a spacecraft that collects a sample of rock or ice or soil or atmosphere, puts it into a container, launches it back, and it lands on Earth so we can study those things in our laboratories here on Earth. And it's relatively easy to do for low gravity bodies without atmospheres like asteroids and comets. It's much more difficult to do it for large moons and planets. Outer satellite orbiter lander, those are things like the moons of Jupiter, the planet-sized moons of Jupiter. Those are really hard to get to just because you have to deal with the huge gravity well of the planet Jupiter or the planet Saturn. It's hard to get a spacecraft to slow down, enter orbit, and then get it to orbit or land on one of the moons. And of course, the most expensive and hardest to do is to send humans to orbit and land on planetary surfaces. So this chart here shows the status of solar system exploration. I haven't updated it because the year just turned. I need to change that to 2022. And you can see across the top the different modes of planetary exploration, from telescopic observations, which is how we discovered everything, all the way out to crewed missions. And then you see we go from Mercury, closest to the sun, all the way out to Pluto and the Kuiper Belt. So you see for flybys, we've done flybys. We've completed the initial reconnaissance of the solar system, which started with Mariner 2 flyby of Venus in 1962, and was completed with the New Horizons flyby of Pluto and in 2015, and then one of the cold classical Kuiper Belt objects, Arrokoth, in January 1st of 2019. As you move across the chart there, you see that we go from more missions have accomplished. We've had lots of orbiters, we've had some landers, we've had a few rovers. We get to robotic sample return, very few, and only the Apollo program to the moon. The things that are written in green are things that are approved and funded and either being constructed or are in operation right now. Those that are in white are past missions that are no longer functioning. Those that are in orange or yellow are things that are conceived but have not yet been fully funded or developed yet, like the Mars sample return. That's what MSR stands for. So there's an awful lot of exciting missions happening now and coming in the next year. And, you can ask me questions about any of those at the end of the talk. I'm going to talk about the Psyche mission right there in the middle. So that's just a preliminary to give you some background on where we're at right now. So in this talk, I'd like to talk about asteroids, what they are, where they're located, why we care about asteroid number 16 Psyche, and what is the nature of the NASA Psyche mission, the objectives of the mission, the instruments, operations, observations, results we hope to obtain, and what we think that'll tell us. And then I'll do a look ahead, and then we'll go to the questions and answers. So you probably know a lot about this. Asteroids, what are they? Asteroids are minor planets, they're protoplanets, they're rocky objects with diameters typically less than 500 kilometers. They're mostly irregularly shaped, like this photo you see here of asteroid Lutetia, imaged by the European Rosetta mission. Irregularly shaped, mostly composed of silicate rock and dust and maybe volatiles. And in this case, the word volatile basically means ices, probably water ice. You might have some more exotic ices like carbon dioxide ice in some places. Where are asteroids located? Well, most of them are in the main asteroid belt located between the orbits of Mars and Jupiter. There's a population at the Lagrange points in Jupiter's orbit around the sun called the Trojan Asteroids. And we just launched in October of last year the Lucy mission to go visit them. The ones that people are the most concerned about are the near-Earth asteroids. And these are the ones that have orbits that come to or cross the Earth's orbit and are potentially hazardous. There's about 4,700 or so of those. And in any given year, there's going to be information. There's going to be flybys of some of these things. And just to show a couple of these from past years, you see here, this slide is referring to one that occurred back in 2013. You see the graphics there, the radar of it, it's an irregular object. The graphic below is showing that it actually flew between the Earth and the Moon's orbit, below the orbit of the geosynchronous satellites even. I'm not going to go into details about this. You can read that off the slides, but this one was expected. It was something that we saw come in. We knew its orbit. We were able to look at it with Earth-based telescopes. This one, about the same size as the one that hit and formed Meteor Crater, which is a 1,200 kilometer diameter crater in northern Arizona, a great place to visit if you ever find yourself coming out to Arizona. This one would have had the destructive power of 2.4 megatons, destruction around 50 miles around it, but not a big civilization ender like the one that killed off the dinosaurs that hit at Chicxulub. That one was 180 kilometer diameter, or excuse me, it produced a 180 kilometer diameter crater. The impactor was thought to be about 10 kilometers in diameter. Those civilization ones are the ones we want to make sure we map and identify. The interesting thing was back in mid-February of 2013, that was the date you probably recall of the Chelyabinsk meteorite explosion over Russia, the largest strike since 1908 Tunguska event. And that one came in same day, but in a different direction, west to east. It wasn't tracked there. It's the one that had the airburst about 12 to 15 miles above ground, a 500 kiloton blast. It, broke some windows, damaged some buildings. There were no fatalities. Initial estimate was $33 million damage. So, these near-Earth asteroids are something to be concerned about, and NASA has a whole program to study near-Earth asteroids, identify the largest ones to progressively smaller ones, map their orbits, and understand what kind of threat they might pose. Then you get fun things like this one. You might remember this one from 2017. Oumuamua is the official name given to this. This object came from outside the solar system, did a close flyby. Some of my faculty colleagues at ASU did some work on it, and they think it was probably a piece of some extrasolar dwarf planet that just happened to come through the solar system. There's more exotic ideas about that, but yeah, we'll leave that there. So in regards to asteroids in our own solar system, what do we know about them? Well, we know a lot about them from the reflected light telescopic spectra. They're classified in different ways. C-types are carbonaceous. They make up most of them. S-types are stony, about 30-35%. The D and P, dark and primitive, tend to be what the Trojans are. V-type is basaltic. It has the same type of rock that comes out of volcanoes like in Hawaii. And asteroid number 4, Vesta, which I worked on the Dawn mission, is one of those. And then there's the M-type. And M in this case stands for metallic, and that's what 16 Psyche is. And we'll talk about more of that. So between the study of reflected light telescopic spectra and the study of meteorites in the laboratories, because meteorites are pieces of asteroids or planets, the consensus is that asteroids are rocks that never coalesce into a planet. The gravitational tides by Jupiter at that particular location inhibited a larger planet from forming. Ceres, number 1 Ceres, is the largest object out there. So in terms of NASA's and the world's spacecraft exploration of asteroids, they really haven't been a focus until more recently in terms of planetary. And by recently, we're going back to the 1960s. They mostly were right-along observations of other spacecraft. The first one imaged up close, 951 Gaspra, was done during the Galileo mission on its cruise out to the outer solar system. I was a grad student at the time those images were acquired, and the same with 243 Ida, where we discovered the first asteroidal moon. The first dedicated asteroid mission was NEAR, which went to 433 Eros in 2000. They actually soft landed on that. The asteroids that are named are in bold on this slide are ones that have had a dedicated mission to actually go. The others were just right along. And so here at the bottom, you see OSIRIS-REx, which is returning its sample, Lucy that just launched to go to the Trojan asteroids, and then Psyche coming next. So this is a great graphic made by the Planetary Society showing all of the large asteroids and comets that were imaged prior to Dawn's arrival at Vesta in 2011. And you can see, as I said, irregularly shaped, heavily cratered. You might see linear features that might be, fractures or grooves, boulders on the surface, etc. Very different from larger planets. So in terms of size comparison, though, here you see the planet Mars, the planet Mercury, Earth's moon, dwarf planet Ceres, and asteroid 4 Vesta to the same size scale there. So asteroids are much smaller than planets. Over here, I want to talk a little bit about the asteroid Psyche and what makes it interesting. So Psyche was the 16th asteroid discovered. It's the largest M-type asteroid in the solar system. It's roughly the shape of sort of a potato. You can see in these shape model maps derived from light curves and telescopic observations, 279 by 232 by 189, or an average, I think, of about 225 kilometer diameter. Discovered by Hannibal de Gasperi of Naples in March of 1852. Psyche orbits at about 2.9 AU, so it's at the outer edge of the main belt. It orbits the sun in about 5 years. It rotates on its axis in a little over 4 hours. What is Psyche composed of? Well, it's M-type, and in this case, M means metal. We think it could be the source of some of the iron meteorites. And here's some examples. I'm sure you've seen iron meteorites before. You have the ones that are they have the Wiedmann pattern, or if they're like a Palasite, they can have olivine grains. We think that occurs near a core mantle boundary. So yeah, basically the thinking is that there could be somewhere in the solar system, some M-type asteroids could be the exposed cores of an asteroid parent body, and Psyche might be the largest. These tend to be much denser, solid bodies. They can have some porosity, which might imply there could be a regolith on the surface. tend to have very little evidence of water ice on them. So how big is 16 Psyche? Well, here you see Vesta and a bunch of smaller asteroids. Lutetia, you recall, was the big one in that first image that I showed. And here is Psyche in comparison to that. So you see, Psyche is smaller than Vesta. Vesta is about the size of Arizona or New Mexico. Psyche is about the size of the state of Massachusetts, or the distance between Phoenix and Flagstaff, if you've ever made that distance. So it's a pretty good size object. And here's just another comparison of Psyche and Vesta. And then if you put Eros close to it, or if you put Bennu next to it, you can see those are much, much smaller. So we're talking a decent sized object. So the NASA Psyche mission is based on a set of driving science questions, because that's what we do when you propose a NASA planetary mission. You're going for the science. What science do you want to accomplish? And the theory is that 16 Psyche could be the exposed core of an asteroid parent body. And to investigate that, we want to look at specific questions. Is Psyche a core, or did it never undergo melting? Is it differentiated, or is it just a piece of unmelted metal? What are the relative ages of its surface regions? Does it contain light elements that would be comparable to what we would find in the Earth's core? Does it have more oxidizing or reducing conditions of formation compared to the Earth's core? And then what kind of topography exists? We have some hint of it from these telescopic maps, but what does it really look like up close and personal? So some basics about the thinking on this. Back early in the history of our solar system, when the gas cloud condensed to small grains and then accumulated to what we call planetesimals of a wide variety, these would have collided and formed embryos, and those embryos would have accreted together to form planets. And the idea is that Psyche was probably one of these where its crust and mantle was knocked off. So imagine a molten planetesimal. So he has a molten iron core, dense silicate crust, and then and denser mantle. You get struck by a hit and run impact that knocks off most of the crust. It exposes the molten metal core to space. It'll start to freeze. And it, of course, will have, since it's rotating, it will have a magnetic field, and then it'll expunge the yellow sulfur from its interior, because sulfur and metal are incompatible. They separate, and eventually you'll freeze. And you could have an exposed core like this. This was the theory about Psyche when we proposed the mission. What does the spacecraft look like? Well, here it looks a lot like an Earth orbiting communication satellite, and there's a reason for that. But basically, you have a box that has computers, and it has flight systems and avionics and electronics, and it has a high gain antenna, and it's going to have thrusters and engines, in this case, ion propulsion engines. And it has this set of booms we call the jungle gym, and that has our science instruments. Here you see a person to scale. So it's not a huge spacecraft, but you see we have magnetometers to measure any magnetic field or remnant magnetic field preserved in the rocks. We have gamma ray and neutron spectrometers, and we have a pair of imaging cameras here. So these will be pointed down at the asteroid as it flies over it. When you deploy the solar panels, you see it's about the size of a tennis court right there. You see 2 wings that'll have 5 solar panels each on it. So what is our mission how's it going to work? Well, we're approaching the launch time frame. The launch window opens on August 1st of 2022. We are going to launch, and with the engines that we have, we're going to fire up our ion engines. We're going to spiral around the sun as we move outward from the Earth. We're going to get a Mars gravity assist in May of 2023. And we're going to fire these ion engines, which thrust for long periods of time, spiraling around until we eventually get out to Psyche in January of 2026. We'll be there for about 21 months or so, with the end of the nominal mission in October of 2027. So it's going to take about a 3.4-year cruise to get out there. Now, on this graphic here, where you see the lines of the trajectory covered in the gray, that is the time of thrusting our ion engines, and I'll explain that in a moment. These dots you see is where we're going to test another instrument on board called Deep Space Optical Communication, or DSOC. We're going to actually use a laser to see if you can use it to transmit information from Earth to the spacecraft as we move out from Earth to Mars orbit and beyond. This will be the first opportunity to test laser optical communications out to that distance. So why are we using ion engines? Well, there's an advantage to using solar electric ion propulsion. The idea is the solar panels take sunlight, convert it into electricity, it powers our spacecraft. We have fuel tanks that contain an inert gas, xenon. You use an electric field to ionize the xenon, you propel the ions against the field, it causes a propulsive force there, and that's what moves the spacecraft. The advantage is this type of fuel is very low in mass, and you always want to have your spacecraft low in mass because the more mass you have, the more expensive it is. If we tried to do this mission with conventional chemical propellant, it would have required a much larger spacecraft. It would have been too expensive to do as a NASA Discovery class mission. So the disadvantage is that the acceleration of these ion engines is very slow. I think it's like 15 miles per hour per day. So it would take 4 days for the spacecraft like this to accelerate from 0 to 60 miles per hour. So your car can do it, very quickly. But the advantage is that this form of propulsion, even though it takes longer to get where you're going, it reduces the mass, reduces the cost of the mission. Now, the type of engine we're using are called Hall thrusters, and they have a lot of experience with the company that made our spacecraft main body, Maxar Technologies, formerly known as Space Systems L'Oreal. They have a long and well-established history of building Earth-orbiting satellites that use this type of thruster to maintain Earth orbit. And this is their first planetary missions they've collaborated with NASA on. So when our spacecraft gets out to the asteroid, it's going to orbit it in a series of orbits. First, of course, as we approach the asteroid, we're going to be looking at it as it gets bigger and bigger in our cameras and search for any moons that it might have, because we know that asteroids can have their own moons. And if it has moons in close orbit, we are not going to be able to get as close as we probably like. I think that's very, very unlikely. We did this at Dawn, the Dawn mission for both Vesta and Ceres, and neither of them had any asteroidal moons there. So we want to be careful in case it does. We'll start off with orbit A at 700 kilometers above the asteroid's surface for about 56 days. And this will give us our, first global reconnaissance with the imager. We'll use it to detect any magnetic fields on the asteroid. Then we're going to drop down to the next orbit, where we'll orbit B at 290 kilometers in altitude. This is where we'll take images and make stereotopography by using the images to study the surface at different look angles, and where I will create a geological map of the surface. At orbit C, we'll drop down even lower, 270 kilometers above the surface. And this is really where it's optimized to get good gravity information. When you have a spacecraft that orbits a planetary body, there can be minor mass concentrations in the body which cause the orbit to be pulled down a little bit. And then when you fly over less mass, it goes back up. You can calculate that very precisely in the Doppler time delay of the radio signals coming back from the spacecraft. And you can use that to build up a gravity model of the interior and determine if it has a mass concentration at its center, like a core. And then on orbit D, the lowest orbit at 85 kilometers in altitude, that's where we're going to do our compositional measurements there. That's where the gamma ray and neutron spectrometer will do their thing and tell us about the composition of it. So this is just that same graphic, and it has a little bit more details. We have the good fortune we're going to be taking images in each of the 4 orbits there, so we're going to get ever increasing resolution of the object as we get close. So we'll be able to characterize the geologic features better and better. But this just says, the reason why we do different orbits is because each one is optimized for a different instrument and for a different set of science goals. Now, what instruments specifically do we have? Well, I talked about imagers, magnetometers, and spectrometers. So the imager, there's going to be 2 of them for redundancy. The imager we're leading at ASU is being built mainly by Malin Space Science Systems in San Diego. They have a long history of building cameras for planetary missions. So the cameras will look down at the surface morphology, or the shape of the surface features, for albedo, which is the brightness and reflected light. And then there's going to be 7 color filters, and they're going to be optimized to identify silicate minerals and possibly even sulfide minerals, because sulfides are often found, in conjunction with metal. Excuse me. We're also going to be able to use the imagers to look down at the surface at different look angles, and that will allow us to develop a stereotopographic map of the surface. Now, the magnetometer is being overseen by MIT, and it's actually not being built by UCLA. It's being built by some international partners at the Danish Technical University north of Copenhagen, Denmark. And they are putting in some very sensitive magnetometers, sensitivity down to 0.1 nanotesla, which is very sensitive for magnetic field measurements, two dual fluxgate magnetometers on a boom. The gamma ray and neutron spectrometers are being built by the Applied Physics Laboratory at Johns Hopkins University near Laurel, Maryland. A gamma ray spectrometer is a type of instrument that measures elemental abundance, particularly things like iron and nickel and silicon and potassium. A neutron spectrometer is really good for measuring hydrogen abundance, which would be akin to any accumulations of water or water ice on the surface. So that will give us our composition. And then, as I described, using the time delay and the radio signals of the spacecraft orbits, we'll do a gravity science experiment, which will allow us to determine the gravitational field of the asteroid. So this is just talking a little bit. As I said, we need some magnetometers. Here they are on the spacecraft. Long heritage. You need imagers. This is the filter wheel and an electronics box. This is just a list for those of you who are familiar with different filters. You might have used some on your telescopes when you look at different planetary objects. So you usually have a broadband clear filter for looking at the surface, and then you have filters for different mineral phases, et cetera. So as I said, silicates and sulfides. This just shows how we'll lay down the footprints of the imager on the surface. So at 35 meters per pixel under orbit A, you see there's relatively big footprints, and we do multiple orbits to cover the whole body. And then you see the footprints get smaller as we move to orbit B, to orbit C, and to orbit D as well. So orbit D, we will not get global coverage at that resolution unless we have an extended mission. And hopefully we will if resources are there. This is just showing examples of what the gamma ray and neutron spectrometers look like. The Applied Physics Lab at Johns Hopkins has built these instruments for many missions, including Messenger and Lunar Prospector, et cetera. And this is just describing the idea of the shape and gravity models of the asteroid from the gravity data we get from orbit. So we get a very accurate shape of the asteroid, better than what we can get from Earth-based telescopes. So how did this whole project actually develop? Well, the first discussions you see here began in 2011. So, over 10 years ago, scientists and some engineers at NASA's Jet Propulsion Laboratory in Pasadena, California, get together, talk about it, decide, yeah, this is something that we think we can actually accomplish. So NASA put out an announcement of opportunity. This is a call for proposals for Discovery-class robotic missions. In 2014, an initial proposal was submitted along with, I think, 28 other proposals. And NASA selected a subset, I believe it was 3 or 4 or 5 proposals to be studied more in depth. And this step 2 was the time where those projects got like $1 million each to refine their proposals. Those were submitted in 2016. And then we got the phone call early in January of 2017 that Psyche was selected, along with Lucy, to be the next 2 Discovery missions, both of them to study asteroids. So since then, the last 5 years, we've been working on the mission. You see over the years, phase B is formulation, preliminary designs. We moved to phases C and D, critical designs, the final designs, and then actually building the hardware. And this ends, I guess I should move this arrow over a little bit because now we are in 2022. And right now the spacecraft is mostly built. Most of the instruments are installed. It's in the clean room at the Jet Propulsion Lab. Right now it's actually in thermovac testing, and I'll talk about that later. So here we are in 2022, preparing for launch in August. And then once we launch, we enter phase E, which is the cruise phase, the operational phase, cruise through the solar system until we arrive at Psyche and begin the actual science phase. So this is just a graphic of one of the early ideas about Psyche, where you get hit and you knock off crust and you have, this molten metal core exposed to space that's actually going to cool. Here's an initial artist concept painting of the asteroid, assuming it was a giant piece of metal. And this is one of the things that I'm most interested in. What does a geological feature look like on a world made out of metal? We know what impact craters look like on rocky worlds, on icy worlds, on dusty worlds. But what would it be like on something which is much more stronger, like metal? You might have projectiles of ejected that are frozen around the craters or something. This graphic is showing, what the possible things the Psyche might be. Did it solidify from the inside out, from the outside in? Is it a giant rubble pile, or is it a piece of unmelted metal left over from the origin of the solar system? So in the 5 years since the mission was selected, a lot of work has been done. Our colleagues who do telescopic observations of solar system objects have trained their telescopes on Psyche. We've tried to refine what we know about it from telescopes to get a better estimate of the effective diameter, the volume of it. That's what these numbers here are telling us. The density range, the mass, all of these are sort of coalescing around 3,000 something kilograms per cubic meter. So we don't think it's a pure metal rock anymore, a pure metal asteroid. We probably think it's got metal, but it's got stuff on it. It could be remnants of silicate crust that fell back onto the asteroid. It could have been carbonaceous chondrite material that are deposited from other carbonaceous asteroid impacts. Perhaps there's even water ice there. There's some evidence to suggest that. This ternary diagram is looking at metal, non-metal silicates probably, and porosity. Porosity means space in between the materials. And you see this line here is what is over here. So it's somewhere in between a metal object and an object that has some sort of material on the surface, and it's probably got at least some amount of non-metal component. That's what this chart is telling us. And that's just some estimates of that based on all the telescopic studies that have been done over the years. So it's basically a bunch of options is what this is telling us there. So we know physical properties from these telescopic observations, thermal inertia, which is resistance to change in temperature, the radar albedo from pointing radar telescopes out of it, and et cetera. So what it suggests is its bulk density is between 3,700 and 4,200 kilograms per cubic meter. So it's much denser than a pure rocky planet. Probably 25 to 60 volume percent metal. So there's still a significant metal component that it has, but it's not uniquely indicated that it's largely metallic. So there's likelihood there's going to be something more on the surface. And so this is what we think, these are another two options of it. You see that same shape of Psyche, but the one on the left here is an artist's concept painting where you have a mostly metal body, but you've got some silicate stuff on the surface. Whereas what you see on the right is that body, but this is where you would have both the silicate and the metal more intimately mixed up. So, if it's all mixed closely together. So any one of these three options could be possible for it, and we won't know until we get there. So how are we going to determine what's what there? Well, there is no one single instrument or one single observation that can answer that question. You're going to have to pull information from all of the different instruments there. So by looking at the abundance from compositional data, are there sulfides and silicates on the surface? Is there a specific nickel content from the gamma ray spectrometer? Is there a magnetic field? You may be able to lay down the evidence to indicate that it could be one of these possibilities here. Another way to look at that is this. So is Psyche a core or primordial unmelted material? Well, looking at the magnetic field here under each of these branches and then looking at the nickel content in each of these, that helps narrow down the possibilities to it. So it's going to be interesting. And the thing we have to remember is on every Planet NASA planetary mission, there's something unexpected occurs. And by that, I mean, we discover something about the body that we had not anticipated before based on our interpretations of the existing data and based on prior models of what it might be. So there's always a possibility that when we get there, it could be something totally different than what these diagrams suggest it might be. Here's an interesting picture. If you take a piece of metal and you use a very powerful gun and fire a metal pellet at it, This is what an impact crater would look like on it, cut in half here. This is made by the vertical gun at NASA Ames Research Center. It's been a device used since the 1960s to fire projectiles of different types into targets of different types to understand the physics of impact crater formation. And you can see here the rim of this crater, it's like frozen on there as a result of that impact. And this is a possible example of what an impact crater could look like on 16 Psyche. Here is a picture of what we call a Palasite Meteorite there. These yellowish things, these are actually grains of olivine. Olivine is a denser silicate mineral rich in iron and magnesium that tends to form in planetary mantles close to the core mantle boundary. And we think when you see this meteorite where you have the olivine grains surrounded by the metal, that this could be from a core mantle boundary someplace in the solar system. Here's what the spacecraft looks like right now. You see the body of the spacecraft. Here are two of the ion engines on this side. Here you see the jungle gym. There's the two magnetometers on the boom on the left. The one on the right here, this is where the gamma ray and neutron spectrometers, they haven't been installed yet at the time that this was taken. And here you see a couple of the fuel tanks inside. Here again is the ion engines. And here is a view of it. And this time you see the interior core. This is where the DSOC, the Deep Space Optical Communications, is going to be. And here's another couple of the thrusters. This was actually, I don't know if I put the date on here. I think these were taken earlier this fall. So right now the spacecraft is in the thermal back chamber at JPL. So they're going to pump the air out of it, and they're going to change the temperature from very hot to very cold and see how the spacecraft's components do. This will be as close as possible to simulating the environment it'll be exposed to in space. And remember, that environment changes because you're going from a relatively warm space environment near Earth to a colder environment as you move out to 2.9 AU. So let me just mention a couple of other things about asteroids and asteroid missions going on. I'm sure you've been following over the years the OSIRIS-REx mission led by the University of Arizona down in Tucson. ASU has a thermal emission imaging instrument on board. It visited the near-Earth asteroid 101955 Bennu. It collected a sample of that, put the sample in a sample return container, and that sample return container is on its way back to Earth. I think it's supposed to land next year. The goal is to characterize and sample what one of these near-Earth primitive asteroids is made out of. The Lucy mission launched in October of last year. Two of our professors, Phil Christensen and Jim Bell at ASU in Phoenix, Tempe, are co-eyes on the mission. They are involved with various instruments. This will be the first robotic mission sent to the Trojan Asteroids of the planet Jupiter, and it's going to do multiple flybys over a 12-year period of various asteroids here in the L4 and the L5 camps. Our first chance to see what these asteroids look like up close. Now, when you think about asteroids, particularly if you're a science fiction fan, you hear about the concept about asteroid mining, actually using them for space resources to help build a spacefaring civilization for humans. We did some estimates for asteroid 16 Psyche based on its known size, based on if it was made out of iron with the appropriate amount of nickel and platinum group elements and things like that, based on what we know from iron meteorites. And our PI, Professor Lindy Elkins-Tanton, calculated that it has metals valued at 100,000 times the GNP of all nations on Earth, or the equivalent of $10,000 quadrillion. Now, that's just a number. If we actually could sample it and bring it back to Earth, the metals market would crash and the value would drop, and it'd be ridiculous. And in fact, we're not a landing mission; we're an orbiter mission, so we're not going to sample the surface at all. So the concept of asteroid mining, as it's talked about, is not really an easy thing to do. It's not going to be like this, where you attach yourself to an asteroid, you suck it in on one side, and you have space stations come out the other side. It's not nearly that easy. It's not nearly, it's something that's going to take a lot of effort over many decades to figure out how humans can work in the microgravity of asteroids to be able to use them. This wonderful graphic by Planetary Resources there does indicate quite well, however, that asteroids, as well as places like the moon, have these space resources. They have iron, they have nickel. They have titanium, like in the case of the lunar mare soils. They may have energy, like helium-3 implanted by the sun. Some of these bodies have water ice preserved on them, which you can use for both oxygen and for rocket fuel. So I think there's a lot of potential in coming decades to take advantage of space resources to help build a spacefaring civilization, but a lot of work needs to be done to take care of that and evaluate that. So that brings me to the conclusion of my talk. Let me summarize the key points here. As you watch the rotating image, this is the best shaped model of asteroid 16 Psyche based on Earth-based telescopes there. And you'll see sort of a northern hemisphere view and a southern hemisphere view. So asteroids are the rocky remnants from the formation of the solar system. On January 4th, 2017, NASA selected Arizona State University to lead a Discovery class robotic mission to the M-class asteroid 16 Psyche. The NASA Psyche spacecraft, which takes a lot of heritage from the Dawn mission of the previous decade, will use solar electric propulsion to move through the solar system and to change our orbits around the asteroid when we get there. Psyche will carry 3 instruments, visible imager, pair of them, 2 magnetometers, and a gamma ray and neutron spectrometer. The Psyche spacecraft, it was built at Maxar Technologies. Additional building has been done at JPL. It is currently there where the instruments and the whole spacecraft is being tested in what we call ATLO, assembly, testing, and launch operations. That's where we're at right now. The launch window opens on August 1st of 2022. It'll have a 3.4-year cruise phase to get to the asteroid, and then a 20-month nominal mission starting in January of 2026. So stay tuned. Keep your eye out for the news as we get into the summer about the plans for launching this. So my next slide is a short movie. I think it plays for just a couple of minutes here. There will be music playing on there. You can just ignore that. It's just music. But this shows a simulation of how the spacecraft will look and the possibility of what the surface of 16 Psyche may look like. All righty, with that, I will stop sharing And I'll conclude and say thank you very much for your attention, and I will be happy to take questions.
All right, thank you very much, Dr. Williams. That was fantastic. We're really looking forward to the mission. We do have a couple of questions in the chat. I don't know if you wanted to start there, and then
Yes.
we can take verbal questions.
Yeah, I'll go ahead and start with the questions in the chat. First one's from Gregory. The extinction of the dinosaurs has now been changed to 66 million years ago. The Chicxulub crater was dated to impact the Earth 66 million years ago by Gerda Keller from Princeton. Yes, that is correct. Could the structure of Psyche be similar to a Mesocederite meteorite? I think it's possible. I think that the conventional wisdom of the team is that it's probably one of the classes of iron meteorite or a Palasite, but yes, that it could be. I don't know whether we'll be able to determine it that cleanly what the composition is. We'll have abundances of the elements. We'll have indications of mineralogy, but it's hopeful that we'll be able to try and link that to a particular meteorite family. And there's colleagues who are specialists in meteorite studies, particularly iron meteorite studies. They're going to help us answer that question. So Rick Bogdanovich, what is the basis for the artist's rendition of Psyche showing two very large and deep adjacent craters? The answer to that is the Earth-based telescopic observations of the asteroid indicate that there are those two large craters there. So, the detailed topography is a little bit unknown, but there are divots in the asteroid, as in that rotating movie during my summary slide. So there's definitely impact craters on the surface, and that's how they know that. Joseph asked, do instruments built in Earth's gravity work differently in places where a gravity field is strong? No, we have a lot of experience building planetary instruments, from imagers to spectrometers to radiometers, that have been tested on Earth, and they factor in the gravity of different bodies. We've tested them on Mars, which has a lower gravity. We've tested them all on the moon, a much lower gravity, and we've obviously tested instruments on asteroids and comets. So there's a pretty good understanding of that, and the instruments that usually work fine. If there's a problem, it could be due to like a solar flare that damages the electronics, or you might have to do a reboot of your computers, the running things. Those are the main types of instruments issues that we've had to deal with. Rich's number 2 question: can there be any form of volcanism on a large metal body such as Psyche, or quaking? I don't think there's earthquakes if the body is completely cooled, and we're expecting objects this small to cool. The smaller a planetary body is, the quicker it's going to lose its heat, and so you're not going to have planetary processes. However, as far as volcanism goes, there are possibilities there. When I first described a cooling metal core, sulfur is immiscible with liquid metal, and that could have extruded onto the surface as sulfur lava flows. Whether they would be preserved after 4.5 billion years is another question. They may not be visible. There's also a theory of something called iron volcanism, where you could have molten regions of liquid metal that squeeze through fractures in the already cooled crust and may come out and flow over there. And there's been some papers published just within the last couple of years of my colleagues suggesting that could exist on Psyche. So that's definitely something that we're going to be looking for. And that's it for the moment for the questions in the chat. Does anybody want to unmute or raise your hand and ask me a question live?
I had a question about the launch vehicle. What launch vehicle is going to be used to launch this into space?
The launch vehicle is going to be a Falcon Heavy by SpaceX. We'll launch a Psyche, and we're also taking another planetary mission with us, a small sat mission. I believe it's called Janus. And I think it's a dual CubeSat mission type of thing. But yeah, NASA, determines the launch vehicle for every mission, and the cost and the proposals that came in, it was determined that SpaceX has the best one. So it'll be a Falcon Heavy.
Thank you.
You're welcome. Other questions?
You mentioned the propulsion is very similar to the Dawn mission. I assume there's no discussion of when you've explored all you can of Psyche, there's no chance of going anywhere else like Dawn did?
Yeah, well, the interesting thing about the Dawn mission, the mission was conceived to visit the two most massive objects in the main asteroid belt. And we went to Vesta first because it was closer in toward Earth. Its orbit is closer than Ceres. But it was designed, and it was actually the solar electric ion propulsion that enabled the Dawn mission, so we could go visit and orbit those two different bodies. At the conclusion of the Dawn mission at Ceres, we still had some resources on board, and we wrote a proposal to NASA about what to do next. And one proposal was to actually depart Ceres and do a slow flyby of another asteroid named Adiona. However, NASA did not select that. They said, the resources of the Dawn mission were really optimized and to do Ceres. So you have another proposal where you can just drop down lower in altitude, get closer to it, and do some very close flybys over those exotic bright spots on Ceres, like the ones in Akator Crater that have the very exotic carbonate, salt-rich, cryovolcanic features on the surface. And so that's what NASA directed us to do. And so that's where we used up the resources to do these very close flyovers of those regions on Ceres. And then the spacecraft was, as it ran out of fuel, was put into a stable orbit. So it should be stable around there for 100 years at least. In the case of the Psyche mission, it's too early to decide what we'll do after we accomplish our goals at Psyche. It's a lot's going to depend on how successfully we are to accomplish what we call the level 1 science objectives and the science goals there. If we manage to get all the answers and there's still a lot of fuel on the spacecraft and power and everything is still working, then we could either depart that and try and go someplace else in the asteroid belt, or we could drop down even lower and try and characterize even better whatever it is we discover at Psyche. So that decision will be made after the nominal mission. Other questions?
I'm wondering if the asteroid, well, maybe asteroids or rocky planetary bodies or terrestrial planetary bodies, is the model that they might have a metal core and a I don't know, rocky silica type surface. And what happened with these metal asteroids is that it got knocked away. I thought maybe you alluded to that at the beginning, but I wasn't quite sure. Is that what the theory is behind the metal asteroids?
Yeah, that's the main idea, is that, you have these planetesimals and some of them form and come together and accrete and make bigger planetoids that then become planets. And, things are banging around in the solar system. Some of them, you're going to have a few very small big ones like Venus and Earth. And then you got maybe a few surviving small ones like Mercury and Mars. But then you have a lot of other ones out there that have differentiated into crust, mantle, and core, iron, nickel cores, silicate mantles, and, rocky crusts. And, some of those, there's always collisions going on out there where you have all this stuff happening. And, you might have had hit and run collisions that knock off a lot of the crust and mantle. And so maybe that is the source of the iron meteorites, is these are exposed cores of some of these asteroid parent bodies. Maybe there was one, I think there was probably multiple of these things out there. Mm-hmm. And that would be a great thing to do if we could link Psyche, 16 Psyche, to one or more of the iron meteorite families.
Okay, thanks.
Mm-hmm.
Remind us of the average distance between asteroids and the main asteroid belt, please.
That is a very good question that I don't happen to know the answer to. But space is a big place, as my old astrophysics professor used to tell me. And so, between individual asteroids, there's a great distance. But Jupiter perturbs the main asteroid belt. You're probably familiar with the resonances that exist out there. And when anything falls in that it's going to eject it. And sometimes it ejects it towards the Earth, the inner solar system. That's where the near-Earth asteroids have come from. Sometimes it'll go into other parts of the belt and it'll smash into things. Just the irregular cratered nature demonstrates, that collisions occur out there all the time. Of course, we're talking also about 4.568 billion years. So, there's a lot of time there. So I don't know the actual distance between individual asteroids out there, but I will say this: every time we've sent a spacecraft to the outer solar system flying through the asteroid belt, we've never hit anything. No micro meteoroids or anything that have damaged, or no spacecraft been lost. So there's still a lot of open space in the main asteroid belt. It's not like Han Solo flying the Millennium Falcon around those asteroids and the Empire Strikes Back. So there's space out there.
Right. Thank you.
I think it's about 400,000 kilometers. I believe that's the average separation of asteroids in the main belt.
Yeah, I was thinking like 600, but thousand. But
I mentioned that in my class. I'd have to check my notes to be sure.
That's why
I think it's 400,000 kilometers.
Yeah.
I have a
Very
question.
Good.
Is Psyche the only asteroid of this type that's known and it has been characterized to whatever degree it has been characterized, or do you know of others of the same type?
Yes, there are others of the M type, the M for metallic. I think Cleopatra is also an M type. Interestingly, the asteroid named after me, 10,461, is also now classified as M-type. When I was given that honor by the International Astronomical Union, along with several other members of the Dawn Vesta team, we were all given Vestoids, the family of asteroids that were formed from the giant impacts on asteroid Vesta, and they're part of the Vestoid family. And then mine was reclassified from V to X, and because X meaning it's different in some way, and then it was reclassified again from X to M. So my asteroid is actually a metallic asteroid. So yeah, there are multiple of them out there. I do not know how many there are, but I do know that there are multiples. I think 16 Psyche and I don't remember the number for it, Cleopatra, are the two largest M class.
And so Psyche was chosen just because it is the one that's known and characterized the most? Is that, or the position of it, or?
I think probably both. I think because it's the largest, it's the one that's probably been studied the most. It's probably the easiest to get to. I think Cleopatra's off the ecliptic or something, or in some way it's a little bit harder to get to. So all of those things factor in about where one would go for things like that. I was on a proposal. We were trying to put together a small sat mission to get to asteroid Pallas, but Pallas is way out of the ecliptic. And so to do that is also a big challenge. So that project didn't move forward. But, there's plenty of things out there that haven't been characterized. Obviously, you're not going to visit everything, but you'd like to visit at least one or two of all of the different class objects out there.
I have two questions. Do you know how big your launch window will be?
I think it's most of the month of August, if I remember correctly. And if there were to be some sort of a technical issue where we couldn't launch in August, we would have a backup opportunity in October of 2022.
And second question, the name of the mission and that body you're visiting are the same, and that seems unusual. What's going on there?
That was just the how it turned out when the initial science team, the PI of this mission is Professor Lindy Elkins Tanton, the former director of our School of Earth and Space Exploration at ASU. She has a long history of studying planetesimals and planetary differentiation and things like that. And rather than try and come up with an acronym, she just decided to name the mission after where we were going. And the other members of the science team agreed with that. I'm actually the last scientist co-investigator that was added to the Step 2 proposal before it was submitted to NASA. Basically, I was added so that I can bring my experience working on planetary missions and experience working on developing planetary geologic maps of the various bodies, so that I would lead that effort on Psyche. So it was just a choice to name the mission after the object where it's going.
I'm just happy there's another NASA anagram we don't have to learn. So that's great. Yeah, there are too many.
The one thing that I've learned in the mission development process, this is actually the first NASA planetary mission where I've been involved in the development phase. There's a whole nother set of acronyms that you have to learn as you go through this, like PDR, preliminary design review, CDR, critical design review, on a whole bunch of them there. And I thought I had learned a lot because just working on the mission when it's active and things, but there's a whole nother thing. It would drive a normal person crazy to try and keep track of all these acronyms. I actually have a PDF file that's like 10 pages long that just lists all of the acronyms and what they stand for.
Somebody in the chat wants to know what's in the case behind you, and I've been curious myself.
Okay, this case here, that is a model of the Rocinante spacecraft from the TV series The Expanse, based on the novels by James S.A. Corey. I'm a big science fiction fan. I was inspired to become a planetary scientist from growing up watching the repeats of the original Star Trek TV series when they were on 5 nights a week through much of the 70s and early 80s. And so I'm a big fan of TV sci-fi. And, so I'm a big Star Trek fan. I'm actually a part of the local Phoenix Star Trek fan club. That's one of the oldest in the country. We've been meeting twice a month since 1975, long before I moved to Arizona. But yeah, science fiction for me has been inspiration for becoming a space scientist, a planetary scientist. And so, yeah, so that's there was a Kickstarter campaign by fans of The Expanse to have a model of the Rocinante. So that's what that is. And then the smaller one here, that's a model of the USS Enterprise, as it appeared in season 2 of Star Trek Discovery. And then that globe up there is a globe of the Jupiter's volcanic moon, Io, the most volcanic object in the solar system. I actually am most known because I made the global geological map of Io from the combined data sets of the Voyager flybys in the 1970s and the Galileo Jupiter orbiter in the late 90s, early 2000s.
Great. There was one more question in the chat.
Let's see. Could you speak a bit about DSOC and its advantages, light versus other forms of communication? Yeah, there's been a desire to develop another mode of communication. The deep space network of radio telescopes that we use, every NASA flight mission has to utilize that. And there are times that it becomes overtaxed, or that the amount of time any given mission has to uplink or downlink information using the DSN is limited. The more missions that are flying, and of course the Europeans and other nations will also use some of that. So there's been a great desire to develop some other mode of communication. And laser optical communication is a promising technology. I think it's been tested from the International Space Station to the Earth and back. So it needs to be tested and see how viable it is as you go further out into the solar system. So that's why it was installed on the Psyche spacecraft. And we're going to do this test to see how well that technology will work as you go from Earth to Mars to outward from that.
All right.
Go ahead.
Any other questions?
I was just wondering, since you mentioned about other countries working like in the European Space Organization there, I wonder what you think the status or characterize how countries are working with each other in missions.
Yes, there has been an awful lot of collaboration with NASA and other international partners for decades. I mean, I think it goes all the way back to Apollo. But on the Galileo mission, which is the first mission I worked on in graduate school closely, we had a lot of international partners. Matter of fact, I don't know if you can see it. That plaque right there, the middle thing is a montage of flags of all the international partners who worked on the Galileo mission. It was actually taken into space by the, yeah, it's right there. So yeah, that one right in the middle, that's all the different flags. So you see the United States and West Germany and Great Britain and France and some others on there. That swatch was taken into space out of the space shuttle Atlantis, and when it launched Galileo in October of 1989. So that's one of my prized possessions. But yeah, there are international instruments that are from European Space Agency, from the Russian Space Agency, from the Canadian Space Agency on various Mars missions. I was a NASA-funded co-investigator on Europe's first Mars orbiter, Mars Express. So there's been international collaboration. On the Dawn mission, we carried a German-built set of framing cameras and an Italian-built visible and infrared spectrometer. In the case of the Psyche mission, we just have a Danish-built set of magnetometers, and then we collaborate with the German Aerospace Center, DLR, and they're going to be helping us create the stereotopographic models from the images of Psyche. So there's collaboration all over the place. You know, we helped the United Arab Emirates launch their first Mars mission. Professor Mark Robinson at ASU has helped the South Koreans develop their camera for their first lunar mission. Basically, there's all sorts of collaboration. The only one that is really out is the People's Republic of China. There's language from the previous decade, the decade of the 2000s, that prevents direct collaboration with the Chinese.
So that preventative measures from our end or their end or both?
I think that is from our end. I mean, you know, data that we generate, obviously the Chinese can have access to it because all NASA planetary data is freely available internationally. And of course, Chinese students can come to US universities and they can work on research projects with the data there, but they're just, I think it has to do with issues of technology, and there's been problems in the past with the Chinese stealing, you know, different types of technology. So that's why that is still in place. Now the scientists themselves, you know, we meet at conferences and we talk about our results. And of course, the Chinese have a very successful lunar exploration program. They've done something nobody else has done. They landed a rover on the far side of the moon. You know, and I'm certain that they're going to have their own astronauts on the moon by the end of this decade. If that help motivates us to complete our return to the moon, so much the better.
Thanks.
I see a couple more questions. Can anyone legally claim ownership of this asteroid? No, I don't think. I think the existing space treaties prevent legal claims on planetary objects. And also, do scientists look above the plane of the solar system for near-Earth objects? Yeah, I believe so. I think the near-Earth object, the NEO program, they're looking in every direction. If there's something dangerous out there, they want to try and identify it, you know, and chart its orbit as well as possible. Other questions?
All right, that sounds like that's it. So I just want to thank you again for joining us. We're really looking forward to the Psyche mission. And maybe in a year or two after the mission begins, we'll have you back to talk about the results.
All righty. Well, yeah, we'll be cruising. We'll test the instruments during the Mars flyby. And yeah, it'll be a few years there, but be happy to chat again sometime.
Great.
Thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
I'll sign off now.
Okay, great. Thanks for joining us.
My pleasure. Everybody have a good weekend.
You too. Happy New Year.
Happy New Year.
Send some of that warmth our way. All right, so let's move on to the president's report. Let me get to my notes here. I wanted to mention the first thing, since we are in a new year, let me share the website here. So give me just a second because I got to move screens around. Here we go. So, of course, hopefully all of you at one time or another have been to the Kalamazoo Astronomical Society website, which I call KAS Online. And of course, you can see the general meeting schedule on the general meeting page, you know, Astrophoto Sig schedule on the Sig page and so on. So you can see the individual schedules here. But of course, a lot of people spend time on the schedule of events page to see what's coming up here. And I just want to remind you, because we pay for this service, is that for each meeting, say you want to go to the like maybe the next Astrophotography Sig meeting on January 21st, and you don't want to take the time to write it down anywhere, but you have your iPhone or your iPad or your computer handy, you can just click on add to calendar. Well, let me scroll down there a bit. And of course, you can add it to your Google Calendar, your Yahoo Calendar, your Outlook Calendar, or your iCalendar. Odds are you have one of these. So you can do that for basically all these activities, just to make sure you get these activities on your schedule so you don't forget, even though I try to remind you as much as I can. But I know a lot of people plan their schedules way in advance. So that's a great way to try to make sure you lock KA stuff in case you find something better to do. But of course, if you find something better to do, you're going to do it anyway, I guess. But we try not to take it personally. And I did want to do a kind of an informal survey here. I don't know if we'll put together another short survey on this, but if you do go through the schedule page, we haven't quite listed a date for the Persian Potluck picnic yet. I know that's not till August. You're probably thinking, why are you talking about this in January? It's because if we do what I'm thinking that we want to do, we have to plan way ahead. So we have two possibilities here. If we still have it at the Kalamazoo Nature Center, we would probably do it on August 6th, because that's the date we also have a public observing session scheduled. So again, we could do it on August 6th at the Nature Center as usual. But for years, I've been wanting to try something different. Maybe go to Van Buren State Park, you know, on the shore of Lake Michigan. They have a nice picnic area there. We could have a picnic, do solar observing, go on the lake shore, take pictures of sunset and all that. And that would be on August 13th, because we can't have it the same day as the observing session, which is again August 6th. So anyone who want to pipe in their opinion here, either verbally or in the chat, would you prefer August 6th at the Nature Center or August 13th at Van Buren State Park?
When does the Perseid showers actually take place?
The peak is usually around August 11th or so, but I think Perseids are mooned out again this year.
Okay.
That's what I've heard.
Then my vote is for Van Buren.
I'll second that.
Okay. That's two.
Third. That's that's August. Excuse me. Which date was that at Van Buren?
13th.
August 13th would be Van Buren State Park, because we don't have a public session that night.
You've got two in the chat to say Van Buren.
Okay.
Yeah, I agree, Van Buren.
Maybe you can vote.
Well, I know Anna would, because that's closer for her. So you don't count.
Might be equidistant for me.
That's true. That's true.
I like the Van Buren idea.
Me too.
Okay. If anybody else wants to chime in, either verbally or in the chat, feel free. You're always welcome to email me as well, in case you don't want to speak up now. But we don't have to do it right away. But if we're going to book something at the picnic area, we need to do that sooner rather than later, because I'm sure those fill up pretty quick. It may be taken already. So, but it's just a thought. I've been wanting to do something different, because we've been at the Nature Center year after year for probably about 2 decades now, I think. So I just feel it's time to try something maybe different, at least for a year.
If nobody pipes up for Nature Center, I don't think necessarily even have to send out a survey. It seems pretty. There seems to be an interest. So
yeah. We can talk about it again next month too. I want to get I would like to hear from more people. There's a lot of people that aren't here tonight, but yeah, it seems like Van Buren seems to be in the lead. So,
and I have a cover for your prime focus for that month.
Oh yeah.
Yeah, specialized for.
Okay. All right. So moving on here, I wanted to give you an update on the remote telescope. Mike Patton installed the new auto guider yesterday. If you've been reading the newsletter, which most of you don't, I'll talk about that later. The new auto guider was installed yesterday. We replaced the Lodestar X2 with a ZWO camera that has like 5.3 times the field of view of the previous camera. And they got both Mike Patton and Jim Kurtz got that focused, and the focus did look pretty good. I got it set up for the plane wave last night, at least the configuration and Maxim DL. So it works with the auto guider, but I'm not sure about the calibration yet. I'm not sure how to preserve the calibration so people don't have to calibrate it over and over and over again, because that would get really boring. So I'm working on that, but it's not set up for the Takahashi yet. So hopefully that'll lead to more reliable capturing of guide stars, because there are certain parts of the sky where guide stars have always been not existent, like with the Helix Nebula, but that's too low to test now, unfortunately. And I wanted to welcome Anna Daly, who is here, and Andy Robbins, who I do not believe is here, but Andy Robbins is fresh off his retirement from WMUK, so he's probably out vacationing and living up life. But I want to welcome Anna and Andy Robbins to the board. You might regret it later, but we'll see.
Well, for now, I'm happy to be here.
All right. It's not that bad. It's really easy. And I want to conclude my president's report. If you looked at the newsletter, I had a obituary in there for Dick Gillespie, but we lost another member recently, KAS member in the late 90s and early 2000s, Dave Moore. Passed away on January 24th. Most of you probably don't know Dave Moore because, again, he was only in the club in the mid 90s to the early 2000s. But Dave Moore did serve as vice president in 1996 and 1997. And if you did read my comprehensive history of Owl Observatory that was in the newsletter a while back, it was a long article because I wanted to get everything in there. I basically give Dave Moore credit for being the main person that really got Owl Observatory off the ground. I know Dave Garden was instrumental in getting it built. Bill Nigg helped with part of the project, but you know, they were around for a long time. So it was really Dave Moore and his sort of get it done and now attitude that got it started with the Nature Center. So that is part of Dave's legacy, and we haven't seen him in quite a while, but he did recently pass away. I don't know if Mumbauer's not here. Pete Mumbauer knew him the best. I was hoping he might be able to say a few words about him, but Sinclair, I know you knew him, and of course he was your vice president when you were president. So did you want to talk about Dave Moore?
Sure. Dave was probably one of well, when I took over as president, we had a very small club, but we had kind of dropped off the map in a lot of ways. We were lucky enough to have some really good board members. Richard joined in, became a board member that year. Dave was my vice president. Richard basically just did a newsletter, but really kind of linked a lot of things together. And it was a driving system. I mean, we just really knew how to work together. And Dave was the guy. He was an engineer who knew how to put stuff together. He built his own roll-off roof observatory down by Vicksburg. Invited us all out there when it was, you know, first light, and he just really knew how to put stuff together. And he was a really strong organizer. And yeah, it's a big loss. I remember having many conversations with Dave after meetings. And a few before meetings about, you know, what direction do you think we should go? And my focus has always been, you know, either it's observational stuff and education, because I'm an educator. Dave's was, we need to build stuff. We need to build things. And he really, really pushed for an observatory. He spent a lot of time negotiating with the Nature Center for the access to the Owl Observatory land, along with Dave Garton. And so I still consider that, you know, of all the people who really played the biggest role in putting together the package that gave us Owl Observatory, Dave Moore was he was like the founding father of the system. So really appreciated his work, and it's a bad loss.
Yeah. Did anyone else want to share anything about Dave Moore? I know most of you did not know him. He was also a pretty good astrophotographer. He took a fantastic image of Hale-Bopp. He traveled all the way out to Arizona to get under dark skies for that, and had a great picture of that back in the film days. It was really good for a film photo. It'd be good for a digital photo today. And we had a lot of great times at his observatory, Astropad, which is out not quite north of Vicksburg. And we were out at Astropad during Hyakutake, when you can see it move across the sky. It came so close to Earth, and so we had a lot of great times at Astropads. Or
I have a great story about Dave,
as Pete called it, the lowlands.
Yeah, the lowlands with all the fog. So Dave was getting ready to make a trip out to Arizona, and I had an LX 200 8-inch telescope. It was one of the early versions. Richard had a bigger one than I did, but Dave needed to take it on an airline. He was going to fly out. And he had two scopes. He borrowed my LX 200, and he had his own. And Dave was one of those who really kind of kept track of stuff. So he got insurance for both those telescopes. Well, only when the airlines flew it out to Arizona, they mashed the mount on that telescope. I mean, they absolutely destroyed it. I don't know how the hell they did it, but somehow they destroyed it. So Dave got insurance that covered the cost of that telescope, bought me, and replaced that telescope with a brand new LX200 that had a GPS built in, which was another like $600 at the time. So I actually got a better telescope out of the airline's dismantling of my telescope. The best part of the story is that when Dave took the remaining telescope back to the airline to say, okay, you guys can have this, they said, no, we don't have any use for it. So he turned around and sold the mirror and the optical tube, which was still intact, and made more money on that telescope than I think anyone's ever made on an LX200. So he thought it out. I got a good telescope. He got a lot of money and replaced the cost of that thing, and he got awesome photographs.
He did.
Well, he deserves 2 thumbs up for that.
Yes. I would try to get more on Dave Moore. That sounds strange. In the next newsletter, hopefully I can get a obituary. Maybe Mumbauer can find it for me. I could try to do an internet search for one, but with a name like Dave Moore, it might be kind of hard to find because it's kind of a common name. But I wish I had a photo of him to share. But back in those days, it was all film, and I didn't take as many pictures of members and stuff as I do today. But I'll see if I can get that put together for the next newsletter. So that's it for the President's Report. Moving on to observing reports. I know we've had a lot of clouds. I never saw it, but did anyone ever get a glimpse at Comet Leonard?
Yeah, I went out one of the very last nights it was supposed to be visible, and it was clear about 15 or 20 degrees above the horizon, but at that time, the comet was, within 5 or 10 degrees of the horizon and set just after dusk. And so there were only 1 or 2 nights that it was possible to see it during that week. And there was a cloud band that stubbornly stuck to the horizon. And it was only 20 degrees when I went out. And it was real cold and real clear. And there was a window, but not in the right place. So no, I didn't see it.
Well,
I tried.
We watched it for over a week out here.
Shut up, Mike. Obviously, you saw it from ASV. That goes without saying. They probably cast shadows on the ground.
Rub it in.
All right. Any other observing reports? We did have some clear skies earlier in the week, but it's cold. Are you? That you?
Can I move back to? I just did a search on the David Moore. I think I picked the right person. If can I share it?
Sure. We'll let you know if it's the right guy.
Share share screen?
Share screen. Yep.
Is he the person?
That's Dave.
That's him.
That's Dave. Yep, that's Dave Moore.
India. Okay.
Well, it says the 23rd there. I was told he died on Christmas Eve, so that's a little better.
But they have a address in Indiana, LaPorte.
All right. Well, don't read all that because I'll try to work on that for the newsletter. But yeah, it was a lot easier to find than I thought because yeah, it's a common name. All right, thanks, Arya. Yeah, that is Dave. At least we can show a picture of him, so that's nice.
Back to, well, I guess I'll share something about Dave first.
Oh yeah, go ahead, Mike.
I remember hanging out at Astropad just like everybody else right after he first built it, and we also went to Niag Fest a couple times together down in with the Michiana group down in wherever it was. I can't remember the name of the town now, but it was like, he was a lot of fun. He was definitely a dedicated observer, liked to take pictures, and he liked to have a good time too. I mean, he was just a fun person to be around, and it's really, really sad that he's gone.
Yep. He did drop a beer bottle in his observatory one time. He told me it was a Nagler, and I believed him. He made me feel stupid, but it was funny.
But in terms of observing reports, I was out just visually the other night. We've had a few clear nights here and there just after sunset, and it's really spectacular just to see the planetary parade in the southwest and southern skies with Jupiter and Saturn and Mercury and Venus and now the moon with all of them. It's just beautiful when we can see them anyways.
Yep.
It just shows, you know, it just shows the path of the ecliptic really, really well. It's just amazing.
Yep, I miss Venus already.
Unfortunately, some of the clearest nights are some of the coldest.
That's the way it works.
Yeah. So
all right.
Duff has one to share.
Okay.
Go ahead.
Wait, I forgot which one it was.
Which one you want to talk about? Constellation or the other one? Which constellation did you see?
I want to do Orion's.
That's fine. Tell that one.
When I was observing last night, I found like 2 nights ago, I found the Orion Nebula.
Sweet.
What's the cluster you found?
It was M33.
Pleiades, M45.
M45.
Okay.
Congratulations.
All right.
Good
Good work.
See? They like it.
I'm jealous. I've not had enough clear skies lately.
And we just laid in the middle of the street and looked at Cassiopeia. We didn't get run over.
All right, moving on here. Let me share this. Astronomical news. This happened on Christmas morning.
Awesome to watch.
Yeah, it was.
I got up live.
Sun shield is deployed.
And then it flew into the clouds and you couldn't see it.
Yeah.
All right, so there we go. We got the launch of the James Webb Space Telescope finally, after who knows how many delays. So yeah, the James Webb launched on December 25th. I don't know how many people got up in the morning to watch it. I had my iPad by my bed and got up and watched it on iPad and tried to get back to sleep for a little while before the present opening stuff commenced. So I did get to watch the launch and some of the NASA coverage. So of course, shortly after launch, when it was in orbit, the solar panels extended. And about a few hours after launch, they did the first mid-course correction burn. They did the second mid-course, or the second course correction on December 27th. And then the first of 3 sun shield layers, of the first 3 sun shield layers were deployed on January 3rd. The last 2 layers, which is all 5, were deployed on January 4th. The secondary mirror structure was deployed on January 5th.
Right.
And then the first primary mirror wing was deployed today, January 7th. The second half of the primary mirror is supposed to unfold tomorrow. And then it'll be in orbit of the L2 point on January 23rd. So that's a quick rundown of where we are with the James Webb Space Telescope. And we should be able to expect the first images probably by June.
Richard, one of the things that was cool on the launch was after the separation of the second stage, they turned on a camera and you could see the solar panel had deployed just before the camera drifted off of view. So that was kind of cool.
Yep.
There were amateur images of the space station, or not space station, but the telescope. But I wanted to get on with the remote telescope to see if I could get it, but I never did. The weather was rough out there in December, so the clear skies weren't plentiful. Any other comments about the James Webb Space Telescope?
What was the event on the 23rd again?
Let me look at my notes. Oh, the 23rd?
Yes.
Oh, that's when of this month. Yeah, that's when Webb will reach the L2 point.
Oh, that's when it reaches the L. Okay. Thank you.
Yeah, no problem. So yeah, that's been a long time coming, and basically, over the next 10 plus years. Oh, they did mention that the first 2 burns were so fuel efficient that Webb will far go past its 10-year expected lifetime. So that's really good news.
Yeah.
Heard that.
You can go to the NASA website and get a timeline of the Webb and watch as everything happens within the timeline of what's going on. That's kind of fun to watch.
Yeah, so basically, over the next 10 years, Webb should reshape astronomy. That's not an understatement. It's going to change a lot. So that's very, very exciting. Any other astronomical news? Okay, I'll mention how many people have seen Don't Look Up on Netflix already?
Not yet.
I did.
If you haven't seen it, see it. It's awesome. If you don't have Netflix, sign up for like the week trial and watch it, because it is a very interesting movie. I thought about writing a review for the newsletter, but we'll see. I have to rewatch it again and take notes as I go through. I might do that tomorrow night. We'll see.
I've watched it 3 times, so I kind of know how this goes.
What's that, Mike? Oh,
he's muted.
Mike, you did it backwards.
Mute. I've watched it 3 times, and every time I watch it, I get more infuriated and angry. I mean, the last time I was yelling at the TV, so maybe I should, maybe I should write that review. I'll write the review for you, Richard. I'll write it, and then you can add things to it if you want.
Okay.
Remind us what it's about.
Okay, so these scientists, these 2 scientists, one, I'm not sure if they're both, but one for sure, who's played by Leonardo DiCaprio, is from Michigan State University. And while working with, I think, the Subaru telescope in Chile, looking for supernovae, stuff like that, they discover a comet. Jennifer Lawrence discovers the comet, and they quickly realize that it's going to collide with Earth. So they, go to the White House, where they're waiting to talk to the president, played by Meryl Streep. They're waiting there for hours. And at one point, a general sells them some snacks. And they find out later that the snacks were free, and Jennifer Lawrence spends the rest of the movie trying to decide, why did he charge us for snacks that were free? This general, but so that's kind of one of the fun parts of the movie. But they basically spend a good chunk of the rest of the movie trying to tell people this comet is coming and it's going to kill us all, but nobody could care less. They just kind of go about their daily business. So it's basically a look at science ignorance. People ignore science, like with climate change, and you can even do modern stuff like vaccinations and stuff like that. So it's basically where a comet's going to hit the Earth. The math absolutely proves it, but people deny it. And of course, I won't tell you how the movie ends, but
I want to tell you my favorite line in the whole movie.
Yeah.
So Tyler Perry is a talk show host, a morning talk show host in New York City. And when Jennifer Lawrence and Leonardo DiCaprio was an astrophysicist at Michigan State University, and Jennifer Lawrence is a PhD student working under him, and they're working on this project, and she's the one who discovers this. And they're being interviewed on this morning talk show host in New York City, which is kind of like, one of the big morning talk show hosts, talk shows. And Tyler Perry's line is when Leonardo DiCaprio mentions that they were working on the Subaru telescope, he says, "I didn't know Subaru made telescopes." That's the best line in the whole movie. That's the one I can really laugh at. Everything else, I just want to choke somebody.
Didn't he say that send that comet to his ex-wife's house?
Yes. My favorite line is when they're trying to coach Leonardo DiCaprio about what to say when he gets on the air. And the guy's like, "Don't talk about math." And he's like, "But it's all math."
Yeah, no math.
Isn't it supposed to be kind of a tongue-in-cheek movie?
It's kind of dark satire.
It's dark satire, yeah.
It's got some
sociological statement.
Yeah, it's pretty
well,
dark in a lot of ways. Like I said, if I actually met people like this and they said the things they say in this movie, I would slap the bejesus out of them. I would slap the living out of them. Notice I used that on perfect timing.
Very good, very good.
Bring your baseball bat.
Yeah, my nurture stick.
Yes.
I thought scientists weren't violent.
Sinclair's the exception to the rule.
There's a few of us out there,
He's a teacher, not a scientist.
That's true. I'm a science teacher. I have a lot of background in science. Yeah, that's a.
There's telescope mirrors out there that would beg to differ with bullet holes in them.
Yeah.
Yeah.
That guy wasn't a scientist, though. I think he was more of an engineer. Some of those engineers are hostile. I'm not even sure he was an engineer. I'm not even sure he could go that far, but yeah. If there's no more astronomical news, I'll move on to the KAS event horizon. We have a observing SIG tomorrow. Aaron, you want to give us an update on that gathering? And what's going on with Richland Township Park? What's the latest on that?
I did not hear back from them. The last time I was up there, they had it locked up. So not sure on the status on that. Looks like the weather tomorrow's not promising. So that takes care of that for us.
Yeah.
I will probably just send out another brief write-up like I do on cloudy days. But we do have another one planned for, I don't even remember when, shortly thereafter.
Yeah, you have to send me the schedule. I don't have the schedule beyond tomorrow.
Oh, okay. Yeah, I'll put that together for you.
Okie dokie. Yeah, so it looks like the SIG isn't going to happen tomorrow, so you can watch Don't Look Up if you haven't seen it yet. Next, we have the Introduction to Amateur Astronomy Lecture Series. Part 1 begins on January 15th at 1:00 p.m. Eastern Standard Time. I am extremely happy to report we currently have 700 people that have registered. That's on par. That's on par with about this time last year. Last year, we had a total of 900 people that registered, but that's it took about several weeks into the lecture series to get to 900. About this time before we started, this is about where we were last time. And we've had clubs all over the US, several in Canada, and this time several in the UK as well. I had some UK people register last time as just kind of an add-on, but this time I focused on the UK, and I've had several come there because for them it starts at 6 o'clock in the evening, so you know it's still a great time for them. But again, we have people in Europe, you know, the rest of Europe. I don't know if I don't think UK considers themselves part of Europe, but we have other European countries. I think we have a handful of people from the Philippines again. Not quite as many countries as last time so far, but still quite a few people around the world. And I've been asking for volunteers to answer questions in the Q&A and also monitor the chat, but I haven't got a whole lot of response on that. So I'm going to revert to the old Richard. And if I think you can do a good job of answering questions in the Q&A, especially for the first part, which is the more technical, sciencey lecture, expect to hear from me very soon. So I'll be hunting people down just like the old days, like what I used to have to do. Then we have an Astrophotography Sig meeting on Friday, January 21st at 8 o'clock. Our guest speaker, gosh, I can't remember his name right now, is, well, I'm on the schedule page here still. Our guest speaker is Bruce Waddington. He'll be speaking on the principles of guiding. So he'll be talking about auto guiding. And he's not the developer because it's open software, but he's one of the heads of the PhD 2 guiding program. And so we're really looking forward to having him. But I want to give those of you that are interested in astrophotography a short warning. So far, you know, we've had people like Jonathan Young and Pete Mumbauer put together excellent presentations, but attendance has been under 20, which is not good enough to keep inviting speakers, whether they be members or guests. So if we don't get up to around the 30 mark that we kind of had for the first SIG meeting last May, the SIG isn't going to survive past this season. So if you've been thinking, well, I skipped some of the meetings, I'm sure everything's fine. Things aren't fine. Again, if we don't get more attendance, I want the attendance to be around 25 to 30. This is going to be it for the Astrophoto SIG because I'm not going to invite people and have hardly anyone show up. So people have to show up. You know, maybe you're thinking, I didn't go to Pete's lecture because I don't have any interest in a Sequence Generator Pro, but I do have an interest in astrophotography. You don't understand what it's like to be in a astronomy club. You just don't attend the things you have an interest in. If you join an astronomy club and you have an interest in astrophotography, even though the subject isn't specifically for you, you attend and you show your support for people that put together these lectures because it is a lot of work to do this. So I just want to remind you what a club is all about. So supporting members, sharing stuff with members. And so I'm afraid the SIG isn't going to make it. So that's just where we're at now. We have part 2 of the lecture series on January 29th. Part 2 is more about constellations and star maps and stuff you can see with just your eyes alone, like, you know, meteor showers, aurora, eclipses, and stuff like that. So part 2 is where the amateur astronomy stuff begins. And then we have an online viewing session on January 29th. And of course, you can register for all this right now on the schedule of events page. And of course, you can add it to your calendar.
Richard, can we go back to the SIG meeting for a minute?
Sure.
Can I forward the invite to the Columbus Club?
Of course.
Okay, great.
I think for the next meeting, we should be okay because I can invite people from the lecture series too, and that'll pull in a lot of people there as well. So, but you know, once we get past the lecture series, you know, we're kind of on our own again. And right now it just ain't working out. Okay, yeah.
Richard, could I jump in
Sure.
while we still have some people here? I just want to make sure to tell Arya that I have the PST and the tripod goes along with it. So if you happen to have a need for it, I mean, I'm happy to keep it and use it, you know, myself, but I just wanted to let Arya know that I have it in my possession.
Okay.
And nobody has contacted me for PST. Actually, it is going between you and Mike Sinclair and Jeff.
Well,
There's a question in the chat asking you to explain the SIG a little more.
Oh, yeah, of course, the SIG is a special interest group on astrophotography. So there's an entire web page about it. I can show you where that is. So let me go back to the website here. We're still on the schedule page. So you can go to the activities menu and pull up the Astrophoto SIG. And basically everything you want to know about the SIG is here. So of course, you know, at SIG meetings, we can share our recent images, but we haven't had too many people, you know, sharing images. We can discuss, you know, equipment, software, do processing demonstrations. We have some guest speakers coming up. Although, speaking of which, our February speaker had to cancel. So I am looking for ideas for a new February speaker. I was thinking something in the realm of planetary imaging, but I haven't had time to look for anybody yet. So if anyone knows of a good speaker for the February meeting, that would be great, because our February speaker had to go to his daughter's university, or will have to do that. So basically the Astrophoto SIG is for anyone interested in astrophotography. So that's what it's all about. It's just like a general meeting, but it's not general. It's all astrophotography. Okay, prime focus. Again, let me share the screen here. I keep doing the wrong thing here. So I hope you all, of course, the cover doesn't look a whole lot different. You can tell it's a little bigger than it used to be. You know, like the margins are a little tighter, because I've decided to ignore margins because people can reduce the page for printing. So who cares about margins? I don't know if there's certain things you realize that you can do with the newsletter. Like, for example, if you want to learn about the general meeting right away, you know, I always have like see page so-and-so for details. And of course, maybe you just kind of scroll through it, but you can, of course, click on see page and woof, there you go. It takes you right to the page. So I don't know if anyone knew it could do that. It's been able to do that for a long time. And of course, I have links to register. I have a link to the website here. So stuff like that. These stupid Zoom controls always get in the way. Oh, that's not the right one. So let me, I cannot use the toolbar at the top because the Zoom stuff gets in the way. But I redesigned the newsletter a little bit, you know, just gave it a facelift so it looks a little bit different. I moved my observations kind of president's column at the front, like most newsletters do. You know, since I started doing the newsletter in 1996, with just a few year break there for a while, I've always had the minutes at the front, but now I have my little president's column here at the front, along with the officers and non-elected people, so you know kind of who does what. I have the minutes here. I really expanded what Aaron gave me this time because I wanted to include Pete's cool panorama of Mauna Kea. And I wanted to include my HR diagram slide. This is the only slide from my talk there. So I'll try to always squeeze this in, but I have a link here to the YouTube video of the meeting. So I'll try to have that for this talk here tonight, where you can just click on the link here and go listen to the meeting on YouTube if you don't want to read all the stuff. And of course, I have the Astrophoto SIG preview there as usual. You know, just kind of scroll through this a bit. Of course, George was nice to include a little review of the Messier Marathon book there, so that was very much appreciated. I threw in something on the James Webb there at the last minute, and I got our NASA space place. I redid the star map a little bit, so I hope you kind of like the updated version of the star map. same map, just a little different layout. And I redesigned the little ad page here. This is the main thing I wanted to mention because I don't know if people know this, but remember you can hover your cursor over the links here. So there's links to the Orion site here. There's links to our clothing page, links to the equipment loan page. There's a link to the contact page here, a link to the gallery page, a link to the Amazon Smile. You get the idea. The only place there's no link is with the Prime Focus here because you just email me. And of course, we have the general meeting preview on the back. So that's just a quick preview of the review of the new newsletter. It's basically the same as the old newsletter, just a little fresh update just to keep it a little lively.
Those of us that are technology challenged are going to have to go back and figure out how to resize the pages when we print it out so it doesn't chop off a whole bunch of stuff.
Yeah, so it's really easy. You just go to print. Oh, I'm not sharing my screen anymore. So let me share my screen again. I forgot I did that.
You just got to click on fit the page. Isn't that all I got to do?
Yep. So you just click fit the page. That's it.
I didn't think to do that, so I have to go back and redo it.
So here's the actual size. Here's the fit the page. It's really easy. Usually it selects fit the page by default. But
some of us are technology challenged.
Yeah. Well, it's good to learn new things. It helps develop new brain cells.
Richard, thanks for including the picture of the cover of the Messier Marathon book. That was.
Yep.
Jack, your technology challenge, you who rappel down buildings and.
It has nothing to do with technology. That's just bravery.
And I just want to mention, now that I use the MailChimp for email, I can keep track of who clicks on what in the emails. And I just want to mention, just because it hurts, it really hurts my feelings. I mean, it really does. I'm not kidding. I sent out 279 versions of that email, or at least MailChimp did. And of the 279 people that got the email with the newsletter, 75 actually clicked on the link. So 75 of 279 people as of today, about 26.9% actually clicked on the link to the newsletter to download it. Now, whether or not every one of those 75 people actually read the thing, I don't know. But so again, maybe the time for a newsletter is over because people just don't look at it.
Well, what makes me feel better, I opened it at least 7 times and I didn't read it once.
Richard, I think that's actually a pretty good number. I do MailChimp for a couple of clubs, and that's actually a pretty good hit rate.
But I would say anything over 10% is actually pretty good.
Yeah.
And you got to remember too, Richard, it's been we're some of us are still coming out of the Christmas break too. So this is not a good time to take a snapshot of that. I don't think this particular site. I don't think I clicked on it
and drive over you several times. You
Well,
do
the
not,
newsletter is a very
you don't
important.
kill that newsletter. You keep it going. That's your
Yeah,
job.
no, I love the newsletter. You got a great newsletter. Just
Those that don't read it are missing out on a lot of good information.
Actually, that's what attracted me to the club. I was so impressed by the newsletter. I decided to investigate, find out more about you guys.
And that's pretty good, Richard. It's
Definitely
only
professional.
January 7th.
I know. Well, I'll keep an eye on it. We'll see how the newsletter clicks go. And
if only 20 and 25% read it, maybe they'll enjoy it enough to make up for the others that don't read it.
Yeah, we'll see. Okay, moving on. Now is the time to mention anything else you wanted to mention. I know Don mentioned the PST. Of course, I can't imagine why no one wants to use it this time of year, but does anyone else have anything they wanted to mention or talk about? Or
I was just on the KAS Sky Shop on Zazzle, and there's a code for 15 to 30% off. So if anybody's waiting to order, now's a good time.
I would also mention, speaking of ordering stuff, if you use Amazon Smile, the KAS will get a piece of that action if you order your stuff through Amazon Smile.
Right.
Yep. Mumbauer's not here, but Mumbauer said he uses Amazon so much we'd be able to get a moon base, and I haven't seen any moon base yet. So,
well, we have had a steady, few dollars each month. So somebody is using it.
Anna, how is that discount on the clothing?
What was that, Jack?
It's a code that's New Year's Gear, years with a Z, of course. NEWYEARZGEAR. You just put it in at checkout. Most of the things are 30% off, but I think a few are 15.
Okay. Cool.
let's see here. Hang on. There we go. They always have sales. You never pay full price for any of the clothing. There's always some sale going on. How come no one's ordered a keychain yet? I'm very upset about that. They're only $3.90.
I literally just ordered one like 5 minutes ago.
Oh wow! I want to see it.
I'll have the only keychain.
I have no idea what these things look like.
Very valuable.
All right, moving on. Preview for next month. If you do not attend next month's meeting, I will have Sinclair run you down with a car and then beat you with his baseball bat. Next month, we have one of the biggest speakers we've ever had. I've been looking forward to having this guy since I joined the club in 1996. So I've been meaning to bring this guy here for a long time. I tried to bring him in 2017, but he was busy. And so I figured now is the time to bring him while we're on Zoom. And I'm hoping to have him in person in 2024. But next month for the February meeting, I think the date is February 4th. We're going to have none other than Professor J.M. Pasikoff from Williams College. He is one of the preeminent eclipse chasers in the entire world. I'm guessing he went to the Antarctica eclipse. So that means he's been to 74 solar eclipses. So this guy is the guy when it comes to chasing down eclipses and talking about the sun and eclipses and everything. And more importantly for me, he wrote, of course, other editions, but mainly the 1983 edition of Peterson's Field Guide to the Stars and Planets that taught me everything about the basics of astronomy. So I've kind of worshiped this guy from afar for a long time because I loved that book growing up. Everyone always asks me, Richard, how'd you learn so much about astronomy? Well, I read Peterson's Field Guide to the Stars and Planets. That's how I learned this stuff. So I'm really looking forward to having him at least on Zoom. I know it's not quite the same as having him on person. He's probably better off that way because I would stalk him like Dan Morgan stalked Story Musgrave one time. Yeah, like Jack Price and I went to Starfest one time, and Dan Morgan followed Story Musgrave, the astronaut, all over the star party. So that would be me with Jay Pasikoff. And just like people not reading the newsletter, if you don't attend next month's meeting, I will take it personally. We got to have 100 and more on YouTube for his visit. I will not accept anything but a sellout for Jay Pasikoff. So register now and be sure you attend because you are not doing anything better that night. So that is the best preview for next month's meeting that I can give. So if there's nothing else, we will go ahead and officially adjourn. So thanks for joining us for the first meeting of the new year.